Hello learners, welcome back to my channel Shraddha's Physics. In this part we will see operational amplifier. That is, here we will see the basic difference between the normal single transistor amplifier with the operational amplifier, and that after we will see its characteristics, and then we will see the difference between an ideal operational amplifier, that is op-amp, and practical operational amplifier. Now let us see the operational amplifier. So the working of operational amplifier, it is quite different from the working of the traditional amplifier. This operational amplifier, it is also known as op-amp. Okay, so in case of normal single transistor amplifier, the input is forward biased and output is reverse biased. And also we can say that in case of, if I will consider for the current, then the current here, it is transferred from the current. In case of the single transistor amplifier, it is transferred from low input impedance to high output impedance to high output impedance. So here we are discussing about the single transistor amplifier. Okay, so from the low input impedance to high input impedance, the current is transferred, and here the signal or the input signal is given across the base emitter junction. So basically we are giving across the base emitter junction. So this is your single transistor amplifier, and you know, if it is common base, then you will get the output across base collector junction, and if it is common emitter, that is, the emitter is common both for your input and output, so you will get output across the emitter and collector, and you have to give the input across the base and emitter. And also you can discuss for your common collector amplifier. So this is all about the single transistor amplifier. Now you can see for the operational amplifier. So in case of the operational amplifier, or here I am writing, in case of op-amp, that is the operational amplifier, more than one transistor and two input signal. Here we will give the two input signals can be given at the terminals at a time. That is, here two input are, in case of the op-amp, we can see there are two input signals. So here you have to give the two input signals at a time. So the design of the amplifier means, here the op-amp, the design of the op-amp is such that it has high input impedance and low output impedance. Okay, so this is the basic difference between the single transistor amplifier and the op-amp. That is, here you can see here the high input impedance and low output impedance, but in case of the single transistor amplifier, you can see, so here the high output impedance and also the low input impedance. Now we will discuss on the block diagram of the operational amplifier. So you can see This is the block diagram of the operational amplifier. One is the inverting terminal and another one is known as the non-inverting. That is, one having negative polarity and other having positive polarity. And this one is your, suppose, input 1 and this one is input 2. So this negative terminal is also known as the inverting terminal. Okay, this one is known as inverting terminal. And this is called, this one is inverting terminal and this plus sign is your non-inverting terminal, and here it is the output. And also in some cases you may find this is your voltage supply, that is your, this is suppose plus V saturation and this is your minus V saturation. Okay, this is your power supply. And also the block diagram may be represented like this. This is your differential amplifier and these are your most stages of gain, and that after it is connected to the class B push pull emitter follower and so on. So here basically we will discuss on these things later. So basically you can see in this case this is the block diagram of the operational amplifier. Here there are two inputs, that is input 1 and input 2. One is the inverting terminal and another one is your non-inverting terminal where you have to give the input, and that after you will get output across this terminal. And we will discuss about what is this basic function of the inverting terminal and non-inverting terminal. Now we will discuss on the properties of op-amp. So this op-amp, it is also known as the multi-stage, it is the multi-stage amplifier. This is the operational amplifier, it is also known as multi-stage amplifier, and also you have seen from the block diagram. And the input stage of op-amp, it is always a differential amplifier. It is a differential amplifier. We will discuss on this type of, that is what is differential amplifier, what is common amplifier, we will discuss on that. This is differential amplifier and it has an inverting input, it has an inverting input and non-inverting input, it has an inverting and non-inverting inputs, non-inverting input. Here you know the high input impedance, here the input impedance is high, high input impedance, and here the low output impedance, it has a very high open loop voltage gain, it has very high open loop voltage gain, open loop voltage gain is very high in case of operational amplifier, and it is always operated with the negative feedback. So these are some important properties of the op-amp. Okay, negative feedback, and it provides constant voltage gain over a wide range of frequency. Okay, it always gives the constant voltage gain over the wide range of frequency, and it has the CMRR value is very large, and the internal stages of the op-amp, they are directly coupled. So this is all about the operational difference between the operational amplifier with the single stage amplifier, and it is the block diagram of the operational amplifier like this, and here it is the, here these are the some properties of the operational amplifier. Now let us draw again the operational amplifier. So here these are the two input terminal, one is the inverting terminal and another one is non-inverting terminal. So here let me write, this is your input 1 and this is your input 2 and this is your output terminal. So here the two input terminals, they have opposite polarity. One is known as, that is this plus one, it is known as the non-inverting terminal, non-inverting terminal, and the negative one implies this is your inverting terminal. So why this term is given to the non-inverting terminal as well as inverting terminal? Because you can see, suppose if I will give, so you can see from this diagram, you can see there are some possibility, that is, if I will say I can give the signal across the input terminal, that is 1, and also I can give the signal across the 2. Individually I can give across the input terminal 1, I can give the signal at once, and in other time I can also give the signal at the positive terminal or the 2 or at the non-inverting terminal, or simultaneously I can give the signal to the both. So these are some basic conditions. So let us first discuss, if I will give signal to the one terminal, that is across the negative terminal, this negative terminal is also known as the inverting terminal. So if I will give the signal like this in the inverting terminal, then this will just try to invert that signal. That is, if I will give the signal like this, then we will get the signal just in the opposite. That is, you can see this positive half is now appear in the negative side, and this negative side will now appear in the positive half, and now the signal get amplified. So that is basically, we can say that if when we will give the signal across the inverting terminal, you will get the signal inverted. But if I will give the signal across, suppose, the non-inverting terminal. So let us discuss about the non-inverting terminal. Suppose I will give the signal like this. Any signal you can give. So suppose the signal is just like this across the positive terminal. So what will happen? Since this is non-inverting terminal, you will get the signal as it is like this. Okay, this negative side will appear on this side as negative, and the positive will appear the same as the positive. So here we can say that in case of the non-inverting terminal, there will be no phase shift across the output. But in case of the inverting terminal, you will get 180 degree phase shift, because for the inverting terminal, if the signal is like this, you will get the signal just having the opposite polarity, you can say, just having the opposite to that of the signal applied. Now we will first discuss on single-ended input op-amp. Single-ended means on the one side of the input, at the one terminal of the input, I will give the signal, and we will see what will happen to this operational amplifier. Suppose this is the operational amplifier like this, and this one is your positive terminal, and this is your negative terminal, means just have to remember this is your inverting terminal, and the inverting terminal, it is grounded, and this one is your non-inverting terminal, and here you have given some input voltage to it, and that after it is being connected to the ground. And here this is the output terminal, that is your V0. Okay. Now this is your non-inverting, and this is your inverting terminal. So here when you give the input signal, this one is your input signal, you will apply it at this point. So here let me write one of the input terminal is grounded and signal, when one of the input terminal is grounded and signal is given at the other end, then it is called single-ended input op-amp or input operational amplifier. Okay. So here at the any one of the input terminal, that is either may be non-inverting and another for may be the inverting terminal, you have to give the signal. Now for suppose here if I will considering for the non-inverting terminal where we have given the signal, suppose in that case, if I will consider for the non-inverting terminal, that is for the non-inverting terminal, if we will give the voltage across the non-inverting terminal, at non-inverting terminal, if the signal is given, then there will be no phase change, across the output, terminal. Okay, so when you will apply the signal across the non-inverting terminal, then there will be no phase change across the outputs. That's why its name is non-inverting. Now you can see that if I will give the signal like this, again I will get the signal like this. That's why it is called the non-inverting signal. It will not invert the signal. Now again, if I will discuss for the inverting signal, so when input signal is given or is applied, if the input signal is applied at the inverting terminal, since it is the inverting terminal, then there will be a phase change of pi between the input and output. Now if I will show you, this is suppose the operational amplifier, and this one is the output, and here this is the input. Here it is the positive terminal and it is the negative terminal, and that is the inverting one. Here I have given the signal across the input, and here the non-inverting terminal, it is being connected to the ground. Now here you can see this is your inverting one, and this is your non-inverting amplifier, non-inverting terminal. Okay. So now if you will apply the signal across this inverting one, now the signal get inverted across the output. So that we can say there will be a 180 degree or phi phase shift between the input and output. But in case of the non-inverting terminal, since the signal that you are given across the input, you will get the same signal across the output, so there will be no phase change. Okay. That is for the non-inverting amplifier. If you will give the signal across the non-inverting amplifier, you will get zero phase shift, or there will be no phase shift across the output terminal. Now we will discuss on double-ended op-amp, double-ended operational amplifier. So double-ended operational amplifier means at the two side, that is at the two input. So let me draw. This is your operational amplifier, just like this, and here these are the two inputs, that is having non-inverting as well as inverting one. Here you have to give the signal common to both the end, and here this one is for the output, and this is your V0. And also we can give the signal, that is, this is suppose the operational amplifier, and here I am giving the signal across the, this is your suppose plus terminal and this one is your minus, and here we have to apply the signal across the inverting as well as the non-inverting. Okay, when we give the signal across the non-inverting as well as the inverting, also we will get an output across this point. Okay, now here we are giving the signal, this is suppose V plus and this is suppose V minus for the inverting terminal. So these are the two cases for the double-ended op-amp. That is, one may be the signal is common to both the input, that is for the inverting one and for the inverting one, and for the non-inverting one the signal is same, or this may be the case, that is the both the signals may be the different. Okay, since this is the double-ended op-amp, we have to give the signal across the both the input. One, it may be the same signal across the both input, or it may be the different signal, that is V plus and V minus across the two input of the op-amp. Okay, now let us write. So when two identical signals are given are given at the two inputs, then the output two signals, of opposite polarities are obtained. So what do you mean by this? So let us consider, you are giving the signal like this, that is across the positive terminal you are giving the signal like this, as well as this is also true for the negative terminal, that is your inverting terminal. When for the two sides, that is for the positive side and the negative side, same signal you are giving. So for the non-inverting terminal you will get the same signal, that is across the output, the same, it will not invert that signal. But in case of the inverting signal, it will give just the inverting output. Okay, but when this get added, that is this output one, we will get the combination of these two. So you can see here, this side negative and this side is positive, since these are your same signal. Okay, so this part is quite similar to this one, but it is just the opposite polarity, one is negative, other is positive one. And for this signal, this one is negative, and here you will get the positive one. Sorry, this is your positive one and this is your negative one, this is the same part. And similarly here for this negative one and this is your positive one. So here if I'll add these two signal, we will get the 0. Okay, so the voltage across this will be 0. When the same type of signal, that is a common signal, is given across this op-amp, that is across the input terminal, you will get the output of the two signal having the opposite polarities. Okay, so we'll discuss it later, that will not exactly will get 0, it is just near to 0. So later we will discuss on that. But if the two input let me write, if the input signals of two inputs differ in phase pi, the two outputs have the same phase. So let us consider, suppose here we are giving the signal like this, and since these are two different signals, here you will give suppose the signal like this, and also you will give the signal, suppose the same type of signal. So let us consider, the two different type of signal. Okay, so when you will give the signal on the non-inverting one, so you will get the same type of output, and for the inverting one you will get the inverted. For the inverting terminal you will get the signal inverted, but when you will add these two, you can see they will be in the same page. Are you getting my point? When you will give the signal like this, and also here the signal is just opposite to that of the signal applied across the non-inverting, and for the non-inverting terminal you will get the same signal as given in the input, but for the inverting terminal you will get just opposite to that of the input applied. But when we will see across the output, these are the combination of these two, so that they will be in the same phase. But in case of the common voltage, or when we will apply the common signal, so here since the two inputs are equally amplified signals in the input, so here it will cancel each other and it will give the 0 output voltage across this. So let me write it here. Yes, let me write here. So for the common side, that is for the common input, here since two inputs are equally amplified, they are equally amplified, or equally amplified signals, we can say equally amplified signals in the input cancels each other, and results to zero output voltage. Zero output voltage. So we can say that if I'll give the signal, that is the same type of signal here, that is one is like this and another one also the same signal is given to the non-inverting as well as the inverting. For the non-inverting you will get the same signal that of your given, and for the inverting it will just get inverted, the signal will get inverted. So here this positive half and this negative half, they will get cancelled, and this negative half and this positive half, they will get cancelled. Or we can say that since they are of just opposite polarity, so these two signal will get added and it will give to zero output voltage. Now let us discuss on the working of the operational amplifier. So one is your common mode operation. So you may draw like this. So this is your operational amplifier, and here is signal is given common to both the terminal. So here this is common signal is applied across the two input and it is being now grounded. Okay. This one is your positive terminal and this is your negative terminal. This one is a non-inverting and this is your inverting terminal, and the output will be across this V0 point. Okay. So now there are two cases. One we will calculate for the when the signal is given for the when the signal is common to both input, and other for the different type of signal that is being given to the two different input. Now let us first discuss for the common mode operation. This is your case 1. This is known as common mode operation. Common mode operation. So common mode means the signal is common to both the terminal. So let us write the signal or the single, let me write the single input signal, the single input signal is common to two inputs and practically we have just discussed, and practically it results to small output, not exactly zero, but it is small output. Okay, so the output is rejected. The output is rejected when a common signal is given to the two inputs. So this phenomenon is known as the common mode rejection. This phenomenon, that is the rejection of the two input, that is called, this phenomenon is known as common mode rejection. This is known as common mode rejection. So this is for the ideal case. You can consider the output to be 0, that is, since we are giving the same signal across the inverting as well as the non-inverting. So in case of the non-inverting, you will get the same type of the signal that you have applied, but in case of the inverting terminal, you will get just the opposite to that of the signal that is being applied. So the combination of this, you will get finally the 0 voltage for the ideal operational amplifier. But in case of the practical op-amp amplifier, this is not exactly 0. We can say that we will get the low output voltage. Okay. Now the next is case 2. We will now discuss for the differential mode operation. Differential mode means when you will give two different inputs across the operational amplifier. So that is called the differential mode. So here we will discuss on the differential mode operation. Now let us draw the operational amplifier just like this. So here one is positive terminal and another one is your negative terminal, and here you have to give the signal across the first terminal. So just a minute. This is your, suppose the signal is given at this point V minus, this is your grounded, and here the signal is given across the non-inverting terminal and it is now grounded, and now you will get the output across this terminal. So in this operation you can write, in this operation the difference between the two signals means the two input signals is amplified in the output. So you'll get an amplified signal, and in the output the two input signals is amplified, and in the output the two output signals are in same phase. They are in the same phase. That is, we have already discussed that if you will apply the signal for the non-inverting terminal, you will get the same one. Since there are two different signals are applied, suppose this is having the opposite polarity, so just like this. So now you will get in the inverting terminal, if you apply the signal, you will get the signal just opposite to that of applied across the inverting terminal. Now the combination of these two output signal, you can get you can see here, they both are in the same phase. So this is called the differential mode operation. Now if I write, suppose V minus and V plus, these are the signal voltage in the fast input. Fast input means your non-inverting one, fast input, and second input respectively. And if I write BD, that is the difference between the two inputs. Difference, if there are two different signal is applied, so this is the BD is the difference between the two inputs. Now we can write the difference between these two will be V minus V plus. Sorry, this is your V plus minus V minus. So this is your V plus minus. Let me correct this. So this is your V plus minus V minus, and the signal here across the input terminal. So this is your fast input. If I will consider, this is your input 1 and this is your input 2. So this will be, for input 1 this is your V plus, for the input 1 this is your V plus fast input, and for the second input we have taken, this is to be V minus. Okay, one is for your non-inverting terminal and another for your inverting terminal. Okay, now here we can also write Vc equal to the common voltage, that is when we are given the common voltage across the two terminals. So for that we can write Vc equal to the common voltage, and it is known as the average voltage also. So this is the combination of these two, that is V plus plus V minus divided by 2, that is the average of this. And if AD represents the differential voltage gain of the amplifier, this is the differential voltage gain of the amplifier, and AC represents the common mode voltage gain of the amplifier. This is the common mode voltage gain of the amplifier. Then we can write VO, that is the output voltage, equal to AD VD plus AC VC. Okay, we will prove this in the next part of this video. So this is equal to V naught equal to AD VD plus AC into VC. VC is the common voltage and VD is the differential voltage of the amplifier. Now you can see in the double-ended op-amp, we have already discussed about this. Now we will see for this one when the two signals are different. Okay, now in this case when these two signals are different, so in one case we may give this is your plus V or this is your plus V voltage we can give, or it may be in other case we can give the plus V signal and the minus V signal. So for that case we have to now calculate mathematically what will be the output voltage in terms of the voltage gain. So now let us calculate the first case for the opposite polarity input. Opposite polarity input. So in this case, that is when the opposite polarity means you have to give, suppose V plus equal to plus V voltage is given, and across the V minus, that is the inverting one, you have supplied suppose minus V voltage. Now here you know Vd equal to the sum, Vd is the differential voltage, that is here I can write the difference between these two, that is V plus minus V minus, that is the differential voltage. So this is equal to, if I will substitute this value, V minus of minus V, that will becomes plus V, that is equal to 2V for the differential voltage. Or similarly, if I will calculate for the common voltage, this is the average voltage V plus V minus divided by 2. So this is equal to V plus is your V, V minus is minus V divided by 2. So that is equal to 0. Now if I will calculate the output voltage, so output voltage you know AD VD plus AC into VC. Now here the voltage gain is AD and VD is your 2V. This is your 2V. Now if I will put this value, this will be 2AD into V. Since this VC equal to 0, so the second term vanishes. So simply I can write, or this V naught can be written as 2VAD. So this is for the opposite polarity input. Now we will discuss for the same polarity input. Suppose the next case, case B is for the same polarity input. Same polarity means just the sign, okay. Same polarity input. Suppose V plus equal to plus V, and here V minus is also plus V. Now we can calculate the differential voltage, that is Vd equal to V plus minus V minus, that is equal to V minus V. If I substitute this value, that is in place of V plus, that is V, and V minus, that is also V. So this is equal to 0. The differential voltage will be 0. So the common voltage will now be equal to V plus V minus divided by 2, the average voltage, that is equal to V plus is V and V minus is also V divided by 2. So that will be 2V by 2, that is equal to V. So now if I will calculate the output voltage we know AD VD plus AC into VC. Since VD equal to 0, now we can write this is equal to, for AC into VC I can simply write this is V into AC, because VC equal to V, or simply we can write VO equal to V into AC. So this is for the same polarity input. Okay, so you can see the difference between when it is having the opposite polarity input. So V naught will be equal to 2VAD, and when it has the same polarity input, the output will be equal to V into AC. So this is all about the introduction of the operational amplifier having its inverting amplifier and non-inverting amplifier connected to the single-ended input or the double-ended input. And also here we have discussed about the working or the operation of the operational amplifier. So in the next part we will see. Now just let me tell you first difference between the ideal op-amp and practical op-amp. That after in the next video we will discuss on the IC 741. So let me tell you what is the difference between the ideal op-amp and practical op-amp. So first of all, in case of the ideal op-amp, this is your for ideal op-amp. If I will draw the operational amplifier for the ideal one, this will be, this is your input one for your non-inverting, and this is your inverting terminal, and here this is AVD. So this is some voltage it is being applied and it is connected to the grounded, and this one is your V plus and this one is your V minus, and here the differential voltage equal to V plus minus V minus. Okay, and this one is your output voltage. And in case of the practical op amp, so for the practical op amp, if I'll draw, so for the practical op amp, so here this is your op amp having input terminal and it is the impedance Zi, and this is your, and here it is the output voltage, and here the input one is your V plus and this is your V minus, and the difference is also here Vd equal to V plus minus V minus. Okay, so what is the difference between an ideal op amp and practical op amp? That is, in case of the ideal op amp, it has, in ideal case we can consider the input impedance that is Zi, you can say, so Zi equal to infinite. And also in this case the output impedance, for the ideal case here I am saying, for the output impedance Zo, that is equal to 0. So it has the voltage gain, we can say the voltage gain here A equal to infinite. But in case of practical op amp, if I will say, here the input impedance as in case of the ideal op amp, it is Zi equal to infinite, but here we can say input impedance is high. Okay, it is not infinite but it is high. We can say the input impedance is very high, and we can say therefore the small input current can be found here. And in case of the output impedance, if I will say, the output impedance for the practical op amp, here in case of the ideal op amp it is 0, but output impedance it is low. It is very low. So it has low output impedance, or we can say the output voltage it is independent of the load value. And in case of the ideal op amp, the voltage gain is infinite, and here in case of the practical op amp, it has very high voltage gain. So it is not infinite, but we can say it is very high voltage gain. So this is the basic difference between the practical op amp and ideal op amp. So here this one is your Zi impedance, this is your Zi. Okay, impedance is given here. Okay, so this is all for today. So in the next lecture we will discuss on IC 741. Thank you all.